Swayam Prabha. Digital India. Educated India.
Okay, so good morning, good afternoon. Welcome back to our series of courses on lectures on analysis and design of rigid pavements. This is lecture 29 of 40, so we're actually very close. We are almost there towards the end, although you may notice we have not actually designed any JPCP as of yet. That's coming up soon. So, as a brief overview, where are we in this class? So, we are on module 4. The topic of module 4 is the mechanistic empirical design of rigid pavements. Module 1 was, of course, an introduction, but it's a very important introduction because we learned two very important aspects. First, we learned the different types of rigid pavements. We learned that there is JPCP, jointed plain concrete pavements, JRCP, jointed reinforced concrete pavements, CRCP, continuously reinforced concrete pavements, and PCP, pre-stressed concrete pavements. Now, of these I had mentioned, JRCP is very rarely used, and PCP is used for more for specialized applications. You can actually find more details about PCP in structural engineering than in pavement engineering. But JPCP is by far the most widely used type of rigid pavement. And so we've actually spent quite a lot of time discussing JPCP. We did have a brief discussion on CRCP also. So CRCP and JPCP, now CRCP is not rarely used. There are actually several examples of it being used. But the reason I mostly focused on JPCP is because, at least as far as analysis is concerned, CRCP and JPCP are very closely tracked to each other. It's only to the point of once we diverge from analysis to design, and we'll talk about what design means in a mechanistic empirical concept. But once we diverge from analysis to design, that's when CRCP and JPCP start to vary. But really, the variance is very specific. It's not too difficult to distinguish between the two. But to a very large extent, the analysis is very similar. So that's why we have, although I haven't said JPCP to CRCP too often, basically we are focusing on JPCP and CRCP simultaneously. Now, that was module 1. Module 2, we had discussed the analysis of rigid pavements using classical methods, and module 3, we had discussed the analysis of rigid pavements using modern finite element methods. So you'll notice 2 modules were devoted to analysis. The reason for this, of course, as I've mentioned previously, is because design is repeated analysis. That is, when you have to do a design, at least the modern concept of design, you have to first choose a trial section, you have to do some analysis, you have to see whether your solution matches against or is less than some required threshold of, say, cracking, faulting, etc., whatever distress, punch outs, whatever distress we're interested in. If not, we go back, we choose a new trial, and we'll talk about, not in today's lecture, a few lectures from now, we'll talk about how we can choose a new trial structure. But we choose a new trial structure and repeat and keep going until we have a satisfactory trial structure, which then becomes a final design. So really, in order to do design, we have to be masters of analysis. And that's why we spent a considerable part of this course on analysis. Now, in the analysis of classical methods, we started off with perhaps the most famous and the most successful method of its time, which was Westergaard's theory. So Professor H.M. Westergaard gave a series of analytical solutions. Analytical solution means under a certain set of assumptions, and there were several assumptions which were made, which we'll talk about in a moment. But under a certain set of assumptions, they provided an exact solution, a simple formula that you can evaluate by hand, you can evaluate on a calculator, maybe you can program into a spreadsheet, but there's no need for any more sophisticated mathematical analysis. Not to say the formulas were easy or straightforward. We actually spent some time solving several of those problems, and we saw a lot of tricks, and you have to be careful not to make calculation errors because they're not very straightforward and easy formulas. But nonetheless, there's no significant mathematical knowledge required in order to implement those formulas. So from Westergaard's theory, we'll also looked at certain updated solutions, which was similar to Westergaard's theory, but simplified some of the assumptions which were made by Westergaard. We also looked at Freiberg theory, which was for dowels. And then we talked about the limitations of these theories. Now, perhaps the biggest limitation of all classical or analytical solutions is the so-called large slab or infinite slab solution. That is, they assume that relative to the load, the joints are very far away. So it could be that the load is at the interior of the slab, in which case all four joints are far away. It could be the load is at the edge, in which case three joints are far away. Or it could be the load is at a corner, in which case two joints are very far away. Now, because of this assumption of the slab being very far away, it is actually possible that Westergaard's theory tends to overestimate this stresses and underestimate deflections. We saw that in one of our earlier slides. There are other assumptions also. So, for example, Westergaard theory, which is primarily a solution to the Sophie-Germain equation with a correction factor applied for a Winkler foundation. So Westergaard's theory assumes that the subgrade, which is modeled as the Winkler foundation, can restrain tension. So what does that mean? Well, it means that if the slab is pushing downwards against the soil, then it faces a reaction force. That's fine. It also means if the slab is moving upwards, if the slab is not pushing but just moving upwards away from the soil, then the soil is pulling the slab back downwards. And as I hope some of you tried this just for the fun of it, when you push your foot against the soil, you can feel a reaction on your knee. When you pull your foot up, however, the soil is not pulling you back. So that was one major shortcoming of the analytical solutions. A third one could possibly be that in the analytical solutions, we had to assume that the loads were circular, or they were, through some corrections later, it was allowed to be square, but that was essentially it. Actual loads, as we saw, tend to be fairly irregular in shape. They tend to have a non-linear pressure distribution, and those sort of complexities cannot be considered using these solutions, at least not very easily using analytical solutions. And then in parallel, the world also kept changing and modern computers started developing much faster. It was in the 1990s onwards that the finite element method started becoming a more popular tool across engineering, including in the engineering of rigid pavements. So what we saw in module 3 was we went into the finite element method. We saw that at its heart, the finite element method makes one assumption. That assumption being that we give up on an analytical solution. We don't even bother trying to get an exact solution. We try to get a weighted residual solutions. We try to minimize a weighted residual solution at certain discrete points, which we call nodes. And then the solution in between those discrete points, we then interpolate using some arbitrary function, which we call shape functions. At what the finite element method does is it takes a partial differential equation and converts it into a series of algebraic equations. And when I say series, as we talked about previously, I don't mean 2 or 3 equations. A typical finite element problem can consist of thousands, tens of thousands, hundreds of thousands, even lakhs of degrees of freedom, as they're called. That is the value that we are solving for. So in those finite element solutions, doing it by hand is essentially impossible. Even doing it on a spreadsheet is more or less difficult, if not impossible. So you do need sophisticated computer programming in order to solve those problems. We also saw how dowels can be incorporated using the component model. How it can be folded into a finite element problem for slabs. And that's really one of the remarkable things about the finite element problem, the ability to combine different types of physics into a relatively straightforward formulation. Now, of course, the dowel lecture was the most complicated lecture we have, so it wasn't that straightforward, but it was still something doable. And more importantly, we saw a particular software called iSlab, which actually implemented all of this. And so we didn't really need to know all of this. It's very important to understand the background of using any tool. But if you just wanted to use the tool and get a solution, you didn't actually have to know all this detail. Okay, so that was module 1, 2, and 3. We have been, for the past couple of lectures, we've been on module 4. Now, module 4 has been on the mechanistic empirical design of rigid pavements. I had defined what is mechanistic empirical design. So, in mechanistic empirical design, we have mechanist, which means mechanics, and then we have empirical, which means based on experience. So, what we do in mechanistic empirical design is we model the pavement using our mechanistic models, which is typically a finite element model today. So we model it using a finite element model. What can we get out of that? Well, we have a slab, we have some subgrade, maybe we have a base layer, we have some loads. From that, we can calculate the stresses, strains, and deflections. That is essentially what we get, at least out of a linear finite element model. Then what happens in mechanistic empirical design is then we also further, still within the realm of mechanistic design, we additionally use the theory of fatigue theory. That is, we do not apply LRFD theory to rigid pavements, we use fatigue theory. And you want to go back to that lecture where we talked about why and what is the logic and the importance of considering fatigue. It's only through fatigue theory that we can actually see some damage or some cracking or distresses occurring in rigid pavements. LRFD does not actually give us any such thing. So the LRFD theory does not, strictly speaking, apply to rigid pavements. So we saw how we can apply what was fatigue theory, which essentially comes down to something called an SN curve. That's sort of a constitutive model from a fatigue theory perspective. So we use we use these mechanics, these principles of mechanics or the mechanistic part of the design to calculate stresses, strains, deflections. From that, we calculate fatigue damage. Now, fatigue damage is the final mechanistic value that we can calculate is fatigue damage. We can sum up the fatigue damage over various climate conditions, over various loads, and finally, that's going to give us the cumulative fatigue damage. And from the cumulative fatigue damage, we can use the empirical part, which is to relate the fatigue damage to whatever distress we're interested in, faulting, cracking, punch outs, etc. So we looked at all this in the previous lectures and we defined transfer functions, which are those empirical part of mechanistic empirical design. Now, in the previous three lectures actually, we have been studying one particular implementation of mechanistic empirical design. I want to highlight that fact. We've been studying AASHTO MEPDG, also called AASHTO Pavement ME, which is by far the most sophisticated, I won't say most widely used, but it is the most sophisticated type of mechanistic empirical design available in the world. It is available for both flexible and rigid pavements, but of course in this class I'm going to stick to discussion on rigid pavements. So AASHTO ME, we talked about its history and we talked about two aspects in the last two lectures. One was traffic characterization and the other was climate characterization. So let me write that down. So we looked at traffic and we looked at climate. Now, for traffic, we saw that in mechanistic empirical design, there is much more we have to do in terms of characterizing traffic than what we used to do in empirical design. In empirical design, we essentially needed to just convert the traffic flow into a number of equivalent standard axes, what in the Indian terminology we call MSA, million standard axes. So we had to convert the traffic into MSA, and that basically was adequate for us in terms of characterizing traffic. In the analysis of rigid pavements in mechanistic empirical principles, however, that's significantly more complicated. We saw that we have basically four types of axles. We have single axles, we have tandem axles, we have tridem axles, and we have quad axles. So we need to know firstly what is our axle configuration. Then we also have to know what is our axle load. What is the load which is carried by each axle, which by the way may not be evenly distributed across the vehicle. We talked about that previously. So such a distribution of load with axle, the distribution of the load for each type of axle is called an axle load spectrum. So we saw axle load spectra previously. And we saw that in India, while we don't have a lot of data on this, we are still working on developing some axle load spectra for different parts of the country. In the US, however, they do have some default values, some measured values, which are later updated from time to time. So as far as the designer is concerned, they at least have some default or some typical traffic values to work with. Now, in the last lecture, we introduced the concept of climate and how climate is affecting JPCP design within the framework of Pavement ME or the AASHTO Mechanistic Empirical Pavement Design Guide. Now, we've actually had 3 lectures on climate in this series of lectures. So, it is a very important aspect. And from these 3 lectures, we learned that essentially when we have some climatic effects, we need to mathematically model them. We learned the methods of doing this mathematical modeling. And perhaps most importantly, out of that entire discussion, we understood that we need to calculate curling stresses. Now, curling stresses occur when two things occur simultaneously. That is, when we have a linear temperature distribution, or at least an equivalent linear temperature distribution. So, if we have a slab and we have some equivalent linear temperature distribution through the depth of the slab, then we know that the slab is going to curl or tends to curl either upwards or downwards depending on the nature of the distribution. On its own, this curling does not cause any stresses. It's only when an external load is applied does a stress develop, and that particular aspect is called curling stresses. So we saw in the previous lecture how ASHTO Pavement ME has a model inside it called the EICM, the Enhanced Integrated Climatic Model. And what the EICM does is it actually calculates at every hour of the analysis. It calculates the temperature profile, which will be a nonlinear profile, through the depth of the pavement for every trial design. Now, what is the typical service life or the analysis period of our design? For rigid pavements, it's 30, 40, 50 years. Now, in 30, 40, 50 years, how many hours are there? Well, let's try to do a quick calculation. So we have 30 years, each year has 365 days. I know there are leap years, I'm just trying to do a rough calculation. And then each day has 24 hours. You can do the calculation, you'll see it goes into lakhs. So there are lakhs upon lakhs of hours in which the temperature distribution is calculated. It's quite a fast model because obviously you can imagine it takes a long time to do these calculations, but it is a very quick, very fast model. In less than 5 minutes, you can probably do this entire analysis. So it calculates this non-linear temperature distribution. And then what we need is we need to be able to simultaneously model the effect of the non-linear temperature distribution as well as an external load. Now, that sounds very straightforward. Our finite element models can do it. It's not particularly difficult conceptually. The problem comes though is because we have a variety of different combinations of loads. We saw we have different types of axles, different axle configurations, different axle load spectra. And we have these lakhs of temperature distributions. The total number of cases we need to run actually goes into trillions and perhaps even more. So we actually reach a problem where although we can do the analysis where we can have a combined effect of temperature as well as a combined effect of loading, practically speaking, it's very difficult to actually perform this analysis. And that brings us, after that somewhat long introduction, it brings us to the topic of today's lecture, which is how do we overcome this very practical problem that we have too many cases that we have to analyze. And the way we overcome it is using a method called linearization. Sometimes this is also written as thermal linearization. So you might add the word thermal up here. So sometimes it's also called thermal linearization. We'll see what it is and what are the advantages. So today we will define linearization and we'll explain the need for it. We'll also solve a quick problem. It's not going to be a finite element problem, so I'm going to give you a lot of notional numbers where I'm just getting some values of stresses, really just out of thin air. It's just, I'm trying to explain the concept. I'm not trying to solve an exact problem over here. So I'll solve a sort of made up linearization problem where you see how it can be solved. And I think then you'll be able to appreciate how much faster linearization makes our entire analysis. Okay, so just as a recollection of what I said, in Pavement ME or in the ASHTO Mechanistic Empirical Pavement Design Guide, traffic is characterized by an axle load spectrum. That's the most important one. So what does an axle load spectrum look like? Well, on the x-axis, we might have axle load. Now, the axle load, the gap between the axle loads, that means that what increments do we have to consider axle loads? That is 10 kilonewtons for single axles, 20 for tandem axles, and 30 for tridem axles. This is the Indian practice. We don't actually have guidance on quad axles. They're anyway very rare in any case. So what we have is at say every 10 kilonewtons, so maybe this will start at 20, then you'll have 30, then you'll have 40. So if this is for single, then at every 10 kilonewtons, you have a mark on the x-axis, and then on the y-axis is what is the observed frequency. So this is frequency, perhaps in percentage. What is the observed frequency of each of these loads? It might look something like this. It doesn't matter what the shape is. This particular thing we have to construct for single axles, for tandem axles, for tridem axles, and for quad axles. And in each case, it's called an axle load spectrum. It needs to be measured in theory. If you're using a full level 1 analysis, you actually have to measure it, you have to estimate it for each project. But generally, at least in the ASHTO approach, you find some typical values which are typical for a state or typical for a particular location, and then you go with those typical values, at least for design, until you can further refine the design. Okay, the other input we needed is axle configuration. So axle configuration is of course single, tandem, tridem. These are axle configurations. But even within say single axle, within each axle we can have single wheel SW or dual wheel. We talked about this. So if this is our axle and we have one wheel on each end of the shaft, that's called a single wheel condition. If we have two wheels on the ends of the shaft, that's called a dual wheel condition. So we have to know what configuration we have. we also need to know what is the spacing between the axes. Even if we've already classified them as single, tandem, tridem, quad, we still have to know what is the spacing between them, because we have to place the loads in our finite element analysis. We have to place the loads somewhere on the slab. And so we need to know what is the configuration of the axis so that we know where to place the load. Additionally, we need to know this information about the axles and the axle distribution. We also need to know what is the total number of vehicles that we are going to be analyzing for over the entire design life. For that, we need two values: ADT, annual average daily traffic. That is the total, that's essentially the total number of vehicles, all vehicles, the total number of vehicles that are expected on a road during a day. So that's the, on average, the number of vehicles on a road during a day when that data is collected annually. So suppose we go out in the field and for 365 days in a given year, we measure for each day what was the amount of traffic that passed through a section, and then we take an average for the daily amount of traffic. That particular number is called AADT, annual average daily traffic. However, as I had mentioned previously, we don't in pavement engineering, we are not really concerned about all the vehicles. In traffic engineering, we are very much concerned about all vehicles. In pavement engineering, we are only really concerned about so-called heavy vehicles. So in the AASHTO classification, that would be called type 4 and above. In the Indian classification, that's type 2 and type 3 and their variations thereof. And in each of them, the reason we are concerned about these heavy vehicles is because the light vehicles, and light vehicles is basically cars, autos, motorbikes, non-motorized vehicles, etc. Each of those is so light that the amount of fatigue damage they cause is negligible. It's either very, very small, or if you are using the concept of endurance limit, which some SN curves have it, some SN curves don't have it. But if you're using the concept of endurance limit, then they almost always, the stress ratio falls below the endurance limit. And therefore, there is technically an infinitely allowable number of repetitions. That's NF is infinite, well, or tends to infinity, and therefore the fatigue damage, which is the number of actual repetitions divided by NF, if NF tends to infinity, then this fatigue damage is basically going to tend to 0. And so there's essentially no fatigue damage caused. So we are really concerned of not AADT, we are actually concerned with the number of vehicles which are class 4 and above, which is buses and trucks. And so there is another number that we are concerned on in traffic inputs, that's AADTT, and this first T over here in this case, this stands for truck. So annual average daily truck traffic, annual average daily traffic, AADT, annual average daily truck traffic, AADTT. So we are more interested in AADTT, and generally we show that as a percentage of the AADT. So for example, we could say that 60% of vehicles are truck, buses and trucks, and so we take AADT, we multiply it by 0.6 and we get AADTT. So that's basically how we do the characterization for the total amount of traffic during analysis. Of course, the amount of traffic during the analysis changes from month to month. Indeed, it also changes for hour to hour. So in the AASHTO pavement ME, we also can have some monthly adjustment factors and some hourly adjustment factors, that we can say that although our baseline AEDT is so much, depending on the month, we may change it by maybe 10 to 15%, or up or down 10-15%. And perhaps for each hour also we can do it. In practice, however, this is very difficult to do. And mostly the monthly and hourly adjustment factors are just set to 1, because it's very difficult to actually get very accurate data. There's a lot of noise basically in the data. You can collect the data, but to statistically distill it into one number is quite a difficult challenge. And finally, we also have to know growth factors, because after all, the amount of traffic does not stay constant. As time changes, as the economy grows, etc., the amount of traffic also increases. So we also have to consider some amount of growth factors. So these are all the traffic inputs that have to be taken into account. Now, the reason I went through such excruciating detail is we have to keep in mind that when we are doing our analysis, each of these specific inputs, these might seem as very small and minor things to think about, but each of these is going to increase the amount of work we have to do and increase the amount of simulations we have to perform in order to do our design. So it's very important to understand all these variations so that we can get a sense of how much effort it takes to actually do one analysis en route to actually doing a full design. Okay, the second thing we talked about was climate characterization. So Pavement ME, I already said this, uses the EICM, Enhanced Integrated Climatic Model, which numerically, what it does is it basically calculates what is the non-linear temperature distribution through the pavement. It does it essentially at a series of points which we defined as nodes. Now, the actual spacing of the nodes depends on the thickness of the pavement. So, the EICM has its own sort of rules. What it does is it puts more nodes near the surface where we expect a larger gradient, and as you go further down, the spacing between the nodes increases. So, there is a non-uniform distribution of these nodes through the pavement thickness. And what the EICM does for PCC. Now, one interesting question I got is this the similar sort of analysis which is done for flexible pavements as well as for rigid pavements? The answer is no. For rigid pavements, so in both cases, it does this calculation, calculates the temperature distribution at a variety of non-uniform nodes, non-uniformly spaced nodes. But in the PCC analysis, so in the flexible pavement analysis, it takes that data and does its own calculation. In the PCC analysis, however, this is interpolated. This is very important. The temperature which is so calculated is actually interpolated at 11 equally spaced points. So let me ask you, if this number of points is 11 and the total thickness is h, what is the spacing of the points? I hope you can do that calculation. The spacing of the points is 0.1 h. That is the logic. Basically, at every 0.1 h, including at the surface, that's where that additional 1 point comes from. You have to take the surface into account. At every 0.1 or every h over 10, a point is added, and at that point, this nonlinear temperature distribution is linearly interpolated. It's a piecewise linear interpolation. This is done at every hour of the analysis period. So I remind you, if the analysis period is 30, and then we have 365 days per year on average, ignoring leap years, and then we have 24 hours per day, and then we have 11 points. This is a very large amount of data which is generated by the EICM. Now, each of these distributions, these are nonlinear distributions. What further happens in the EICM is these nonlinear distributions are then decomposed, and we talked about this just now, into an equivalent linear temperature gradient. So, it's ELTG term. You see me use this once in a while. It's used in a lot of literature. So, let me just write it down. I don't think I defined this before. So, this is equivalent linear temperature gradient. It is that delta TL divided by H. We saw TL previously. We saw how to derive TL. We had a long lecture on that, and we did an example also. So please go back and review that lecture in case you don't recall. Delta T was top temperature minus bottom temperature. That's always the definition of delta T, top minus bottom. You divide it by the total thickness, you basically get the slope of that line, and that slope is the equivalent linear temperature gradient. Furthermore, the EICM also decomposes this. Actually, Pavement ME, the EICM doesn't do this. Pavement ME takes this nonlinear temperature distribution, it gets us an ELTG. That ELTG has to be used for curling, and that's going to be the topic of today's lecture. But it is also used to calculate the nonlinear components, which we had previously said gives rise to eigenstresses. So again, please go back to that lecture and review it and make sure you fully understand the difference between curling and eigenstresses. It's an important distinction to keep in mind. Okay. Now, as we talked about, the stresses in JPCP that are developed, which primarily is what we're interested in. We take stress, from stress we calculate stress ratio. From stress ratio, we use an SN curve to calculate the allowable repetitions. From that, plus traffic information, we calculate fatigue damage. And fatigue damage is basically where our mechanistic part of our design ends. And later we use a transfer function and convert it into some sort of distress. So stresses are really the basic thing we're trying to calculate. So stresses in JPCP are developed due to, we talked about this previously, it is due to climate, and climate we defined as curling, eigenstresses. So those are the two transient temperature distribution effects. We also mentioned that there is a BIC which was built-in curling, and I mentioned this in Indian practice. This is also sometimes called the zero stress temperature gradient or temperature difference. So that's in other applications, particularly in North America, it's called BIC, built-in curling. They mean the same thing. It's sort of the permanent temperature difference which is built into the pavement as it went from its fresh state into its hardened state. Okay, and then there was of course moisture effect also. We talked about moisture effect. We looked at Bajant and Baweja B3 model, and we did an example of it also. So please go back to those lectures in case you don't recall it. But we saw that eventually moisture is converted into some kind of a fictitious temperature, which we call a shrinkage temperature. It's not a real temperature, you can't actually measure it, but it's a fictitious temperature, and so it's also added into this transient temperature distribution and built-in curling, and then we can do the calculations accordingly. So one cause of stresses developing in JPCP is climate. The other cause, of course, is traffic, which we just talked about. The key thing to keep in mind, which is really, that's what comes out, and we'll talk about when we get to IRC 58, we'll see even there, it was only around 10 years ago that this aspect was also incorporated. The key distinction which comes over here is these two factors act simultaneously. So as I had pointed out previously, if we have just a linear temperature distribution, on its own it doesn't cause any stress. You have to have an external load which is also acting, and the combined effect of the temperature distribution as well as the external load, that is what generates stress. Of course, we do have eigenstress separately. So eigenstress, again, go back and review that lecture, but eigenstress is a sort of characteristic stress. It does not depend on any external load. So we can always calculate eigenstress directly, but in order to calculate curling stress, not only do we have to know the magnitude of this delta TL, not only do we have to know traffic, we have to be able to model both of these two simultaneously on the pavement. And it is really that point of simultaneity that we're going to talk about in today's lecture that leads to quite a lot of difficulties. So the issue is as follows. The simultaneous knowledge of traffic loads and climate well into the future, again we're talking 30 to 50 years into the future, simultaneously being able to say that at a particular hour, this is the exact temperature distribution that's going to be developed, and this is the exact traffic load distribution, that the axle load spectrum that is going to occur at that hour on the pavement. To say this, both of these two pieces of information with confidence 30 to 50 years into the future is actually quite difficult. There is a lot of statistical noise in this process. There's a lot of uncertainty that we cannot foresee. So it's actually very difficult to have simultaneous knowledge of traffic loads as well as climate into the future. That's one problem. Now, one thing to keep in mind is when we're talking about the effect of climate and curling, I had mentioned this previously, so let me reiterate it. There are two effects we are concerned with, which is we call bottom-up cracking and top-down cracking. So when we have this delta TL, this equivalent linear temperature gradient or difference, when it's greater than 0, that basically means the T top is greater than the T bottom. Then we get this sort of a shape that pavement tends to take. It doesn't actually take, but it tends to take this sort of a shape. Then when you have a load in the middle, the pavement is restrained from taking this sort of a shape, and that's what leads to generation of a tensile stress at the bottom surface, and that eventually leads to a small amount of micro cracking, and that crack eventually grows from the bottom to the top upwards. Hence we call that bottom up cracking. Now this generally happens during the day. During the night, we have the opposite effects, that we have delta TL, which is actually less than 0. In that case, the pavement takes this type of a shape, this sort of concave upwards type of shape. And so what we have is that when we have a load which is as follows, the load is essentially at the two ends, not in the middle, but at the two ends, then the pavement is restrained from taking the shape, and a tensile stress occurs over here at this critical point. So this is at the top surface. One repetition leads to a small amount of damage, a few micro cracks. As you have thousands to millions of repetitions, a macro crack starts forming, and that's what we call a top-down crack. So the thing to understand in JPCP, and we'll come back to this also subsequently, the thing to understand in JPCP is that we actually have to do two sets of analysis. We have to separately analyze bottom-up cracking, and we have to separately analyze top-down cracking. So as we calculate from the EICM, we get the temperature distributions. From there, when we split up the temperature distribution into the components, and we get the equivalent linear temperature distribution, and from there we get ELTG, or this delta TL. Based on that, depending on whether it's positive or negative, we have to break it down and decide and analyze it either as a bottom-up case or as a top-down case, and we have to do the analysis separately. Okay. So, given the difficulty in characterizing traffic at an hourly level, so because it's very difficult to accurately understand what sort of traffic is going to occur at an hourly level well into the future, also given that there are always some uncertainties in the EICM calculation. It's a numerical method, so it's not to be that it's always going to be correct. There will be some errors in it. Pavement ME actually develops what we call monthly combined distribution of traffic loads and temperature differences. So instead of having to know what is the actual traffic and actual temperature difference at every hour, what Pavement ME does, it actually generates a probability distribution. We'll see more about how it's done today. It generates a probability distribution, and this is a joint probability distribution. What it says is, for a given traffic load, this is the probability of having a particular temperature difference. And it uses that, instead of actually analyzing at every hour, it uses this probability distribution to calculate an average or expected value of the stress at each load level. This process is called linearization, or sometimes also called thermal linearization. So it overcomes at a fundamental level, it overcomes the biggest theoretical issue, which is this large amount of uncertainty in knowing the temperature distribution as well as the traffic at exactly the same time. As we shall see, an additional advantage that it gives us is it significantly reduces the number of cases we have to analyze, and that is also an important consideration. We'll see more about that a couple of lectures from now when we talk about design optimization. Okay, so let's go through what is the process of this linearization or thermal linearization. Again, what you want to remember is at this point, before we do linearization, we have two things. We have the at every hour, we have this delta TL, which we've calculated, and we also have the eigenstresses. So we have calculated both of these at every hour. Separately, keep in mind, we also still have built-in curling and we have moisture effects. So let me just write that as TSH. So we also have these effects that we have to think about. Okay, so at every hour we have these. We also have some knowledge of traffic. So we've got traffic, which is our axle load distribution as well as our axle configuration. So we've got some knowledge of that. At an hourly level, it's quite difficult to have that knowledge, but at least at a monthly level, we certainly have that knowledge. Okay, so the first step is as follows. The first step surprisingly doesn't even take this data into account. The first step of linearization is interestingly a pre-processing step. And the pre-processing step is as follows. What it says is establish a table of linear temperature difference at approximately every 1 degree Celsius. By the way, I say approximately because the exact units, if you actually go into the MEPDG documentation, which I'll show you some pictures of in a moment, the exact units, it actually says 2 degrees Fahrenheit, because in the US they use Fahrenheit. So it actually says that every 2 degree Fahrenheit, you have to construct a table. That's approximately, not exactly, actually 1.8 degree Fahrenheit will actually give you 1 degree Celsius, but roughly that's every 1 degree Celsius. So that's why I've written approximately every 1 degree Celsius. So establish a table of linear temperature differences at approximately every 1 degree Celsius. So you basically create a table. I'll show you the table in the next slide. So I've got it in an example. So you create a table where you have, okay, 0 degree Celsius, 1 degree Celsius, 2 degree Celsius, and then on the negative side, minus 1 degree Celsius, minus 2 degree Celsius, minus 3, so on. So create this type of a table where you are stating that assume that our JPCP section has this linear temperature difference. Ignore the non-linear component. Assume it has a linear temperature difference. And then for each of those linear temperature differences, what the pavement ME does is it calculates the critical stresses for some reference load configuration. So as I said, this is a pre-processing step. It actually does not depend on the actual traffic, nor does it depend on the actual temperature distribution. This is done completely separate of the actual problem that we are solving. So first of all, we don't look at the actual temperature difference. We actually choose some discrete values at every 1 degree Celsius. We choose some discrete values of some linear temperature difference. Then we also take some reference traffic. I'll show you in a second what the reference traffic is, but to keep in mind, the reference traffic or the reference type of load is essentially an arbitrary choice. It's not a bad choice per se, it is fairly representative, but we'll see it is more or less it is arbitrary. So the reference load is somewhat arbitrary. So what we do is we take this for every degree Celsius change in the temperature difference, we then calculate what is the critical stress for this reference load. So let's have a look at what this reference load is. So the reference load, of course, depends on what analysis we're doing, what type of distress are we trying to calculate. If you're trying to calculate fatigue cracking, then as I just said, we have to separately look at bottom-up cracking and we have to separately look at top-down cracking. So let's look at bottom-up cracking. So the reference load for bottom-up cracking is what I've shown in this diagram. This is taken directly from the Pavement ME documentation. So what we have here is we have a shoulder. Normally, traffic should not be going on the shoulder. So in our pavement analysis, we assume that there's no traffic on the shoulder. We have this single axle load. If you look carefully, you will notice this is this SASW condition. This is a single axle, sorry, SASDW. This is a single axle dual wheel because you can see these two tires are present and it's just one axle, so it's a single axle. So we have this single axle load which is in what we call the traffic lane. It consists of the following. It consists of an 80 kilonewton single wheel with dual tires. So that means the total load on this axle is 80 kilonewtons. You want to go back 2 lectures previously, we had done this quick calculation. In that case, what is the load applied by each tire? Well, that's simply 80 divided by 4, that's 20 kilonewton. So each tire is basically applying 20 kilonewton. The total axle is applying 80 kilonewtons. And this is further placed as follows. It is placed in the longitudinal direction. It is placed at halfway between the transverse joints. So it's placed at exactly the middle of the slab, and in the transverse direction it is placed with a slight displacement of, and this is around 525 millimeters from the edge. So this is roughly 525 millimeters. Why this value we will actually not talk about in today's lecture. We'll see a few lectures from now when we talk about wander. So just hold on to that, but just for now understand that we place it at this distance 525 millimeter from the edge. It so turns out this is our critical configuration for bottom up cracking. So where you have this little red blow up thing which is over here, as marked over here, this is the critical location which is at the bottom of the slab. So when you place the axle in this configuration, this leads to a critical stress developing at this point on the slab. So that's the reference traffic. It's just one axle, by the way. It's the reference traffic for bottom up cracking. Now if you look at for top down cracking, the reference condition consists of three axles. It consists of a single axle, and the single axle is 54 kilonewtons, and it consists of a tandem axle which is 150 kilonewtons. Both of them are dual wheel. So over here we have a single axle dual wheel, and we have a tandem axle dual wheel. So it's mentioned over here, this is 150 kilonewtons. You can do this calculation again. So what is the load on each tire? Well, if you look at it, each of the axles within the tandem axle has 4 tires. So totally we have 8 tires. 150 over 8, you can do the calculation. That basically is the load on each tire. Okay. So this is the reference configuration, that we have a single axle and we have a tandem axle dual wheel, a tandem axle. Both of them have dual wheels, and they are placed as follows, as shown over here. The single axle is actually placed on the transverse joint, so it's placed just at the transverse joint, and the tandem axle is placed such that the first wheel of the tandem axle is very close to the other transverse joint, and the second wheel is actually on the other slab altogether. So we've got the single axle here which is on the transverse joint. We've got the first wheel of the tandem axle which is placed very close to the second transverse joint, and then the other one which is actually on the other slab altogether. In this condition, the critical location where the stress is developed, again this is for top down cracking, so this is where the stress is developed at the top of the slab, is as marked over here. It's actually in the middle of the slab at the top surface, and that's actually why this particular configuration was chosen, so that around approximately in the middle of the edge of the slab, that's where we get the maximum stress. By the way, they are placed in such a way to maximize critical stress. So over here we saw that they are placed at, the axle is placed at a distance of 525 mm from the longitudinal edge. In the case of top down cracking, it turns out the critical condition occurs when it is placed exactly at the longitudinal edge. So in this case, we don't have the additional 525 mm. Okay. So in the process of linearizations, again we have to do top down cracking and bottom up cracking separately. So in the process of linearization, we have to construct a table as follows, separately for bottom up and top down cracking. So over here we have for bottom up cracking at every 1 degree Celsius. So bottom up cracking occurs when this delta TL is greater than 0. So for every 1 degree Celsius change, we enumerate a table. So we fill here, I've done a 1, 2, 3, 4. It's generally difficult to get above 4 degrees Celsius temperature difference. That's quite a lot. It's not impossible, but it's quite a lot. Okay, and similarly on the top down side, in top down cracking, delta TL has to be less than 0. So I've got -1, -2, -3, -4. So I've created these numbers. Then what we do is for bottom up cracking, for this axle load configuration, and then whatever the other inputs are. So whatever the thickness of the slab is, whatever the material properties of the slab is, whatever the properties of the subgrade, base layer, etc. Whatever the design structure is, for that design structure, for that value of delta T for bottom up cracking, the load is applied as I showed in this figure, and the critical stress for bottom up condition, the critical stress is extracted using the finite element model. We actually don't use a finite element model in pavement ME. We use a neural network instead. We'll talk about that, I think, in the next lecture. Okay. And then similarly, for when delta TL is less than 0, that is we have top down cracking, then again depending on what are the input conditions for the slab, the load is placed as shown over here, and the critical stress, this time at the top of the slab, is extracted. So what we can then populate these second columns for each for bottom up cracking and for top down cracking, which is the critical stress. Now I should emphasize that what I've put over here in this table, which I'm calling table A, what in this table A, these are notional values, right? So I haven't actually done the calculation and I'm not giving you the exact answer. So if you actually analyzed it for a particular pavement, there's a good chance you'll get a significantly different answer. Nonetheless, I think these are somewhat reasonable numbers. That's why I put them over there. It's based mostly on my experience. Okay, so what we see over here is obviously as you increase this delta t, the critical load is going to increase. So what I did here, as delta t increases, I put an increasing value of this critical stress. Again, these are notional values, I haven't calculated them, but this trend is generally what you will see in practice. Similarly, as the magnitude of delta TL increases, even for top-down cracking, the critical stress will also increase. And so I have put some notional values to show critical stress in top-down cracking. Now, what you want to note here is we have applied this delta TL in this case. So that is, we applied a linear temperature distribution to a slab and then we did this calculation. Eigenstresses in this case are 0, because eigenstresses only occurred when you have a non-linear temperature distribution. So because in this case the temperature distribution is purely linear, that's what we are assuming the nature of the temperature distribution is. Because this assumed temperature distribution is purely linear, the eigenstresses are 0. So we don't have to account for that in this calculation. So that was step 1. At the end of step 1, we get this table. This is actually a pre-processing step. It can be done even before the rest of the analysis is done. So we get this table for bottom up and top down separately. For each value of delta TL, we get the critical stress for the reference load. Okay. Step 2 goes as follows. For the same reference load, again, we haven't seen our actual traffic yet. For the same reference load, determine the stress corresponding to the actual non-linear temperature profile at each hour. So previously, as we saw, for every month, this analysis is done, by the way, monthly. So for at every month, we get an actual temperature distribution T, which is non-linear in nature. We can decompose it into its components, the eigenstress component, the non-linear component, as well as the linear component. So for this non-linear temperature distribution, what step 2 says is, at each hour of a given month, this whole analysis is only done month by month. At each hour of a given month, do not consider the actual traffic, but consider the reference traffic. Place the load for the reference traffic, assuming that you have this actual calculated non-linear temperature distribution, and then calculate what are the critical stresses that come out due to this real temperature distribution, or real to the extent that has been calculated for this particular analysis. So calculate it for this particular temperature distribution and then calculate the stresses out of that for the reference loads. We still have not calculated for our actual axial load spectrum yet. We'll get to that. What's also recommended is, in this case, this actual temperature distribution TZ, this also needs to take into account the zero stress temperature difference, which was this built-in curling. So built-in curling and moisture effects need to be added to this previously. So we might have a T of Z, which is our transient temperature distribution. EICM calculates that. To that, we add the built-in curling, whatever that distribution that is. To that, we also add this TSH, which is the moisture. So this is what I mean by the total effective temperature, which is through the temperature, which is through the pavement. So we will then get a table as follows. So a particular analysis for a particular month of the analysis. For example, June 1998, I just pulled out a particular month. For a particular month of the analysis, we will get the following table. This is what I'm calling table B. By the way, just before I go into table B, table A does not depend on any particular month. It's a pure pre-processing step. It doesn't matter which month these assumed temperature differences occur. It's going to stay the same for all months. So table A is completely pre-processed. It only has to be calculated once. Table B consists of the follows. For the given month, for each day of the month, and for each hour of the month. So totally, we're actually going to get approximately 30 or 31 into 24, that's around 720. So we actually have roughly 720 cases that we have to account for. So for each day of the month and for each hour, what you do is you take the actual temperature distribution, and then for that actual temperature distribution, again, actual temperature distribution is what I just showed over here. It's the transient plus the BIC plus the shrinkage. Take the actual temperature distribution and, using ISLAB or any numerical analysis program, calculate what are the critical stresses and also classify the mode of those stresses, that is it top down or is it bottom up. You may notice here for these hours 0, 1, 2. So 0, by the way, is corresponds to midnight. That's the convention in the EICM. So at midnight, at 1 a.m. and 2 a.m., you notice I put top down. That's what you would expect. And this is 13, 14, which is 1 p.m. and 2 p.m. There, I put these as bottom up. So that is, although these are notional values, I'm fairly sure that the values are pretty reasonable for the reasons that I explained. So for each hour, for those reference loads, we still haven't used our actual traffic loads. So for those reference loads, for each hour of the month, use IceLab or use the numerical analysis tool and then calculate what are the critical stresses, note down the critical stresses as well as the mode of the stress, that is whether it's top down or bottom up. So we call this table as table B. Step 3 is actually the most innovative step. This is where we actually start combining our actual traffic with the observed distributions. So step 3 and step 4 is now when we start bringing both of them together. For each of the stresses which were developed in table B, you want to know the stresses in table B are for the actual temperature distributions. They do include eigenstresses. So the eigenstresses are not but may not be 0 in this case. Whereas for table A, the eigenstresses are always going to be exactly 0. Okay, so for each of these total stresses which are calculated in table B, look up the temperature difference range from table A such that the actual nonlinear temperature difference, actual nonlinear temperature distribution, I should add, not difference, actual nonlinear temperature distribution and the assumed linear temperature difference give the same stress. Okay, let me actually explain that through showing you this example. So again, this is very similar to table B, except I just added one more column. So here for each hour, I calculated the stress. I also checked what type of stress do I have. Is it top down or bottom up? What step 3 actually says is, you take this stress. This is the stress from table B. That's the stress for the reference load, but the actual temperature distribution. Take that stress and then look up that stress value in table A. So let me go back to table C for a second. So what we see is the stress in this case, the one I circled, is 0.98 megapascals and it is in top down mode. Top down, we know that delta TL has to be less than 0. So just keep this number 0.98 in mind and let's go back to table A. Table A, okay, we are talking about top down cracking, so we look at this half of table A and we look up what this value 0.98, where does it fall within this temperature range. So we see that 0.98 is between 0.97 and 1.63. So somewhere between -2 and -3 degrees Celsius of an assumed linear temperature difference, we would get the stress of 0.98. The 0.98 is the stress we get for the actual temperature distribution for that month and for that hour. So that means for the 0.98 is going to occur somewhere between -2 and -3 degrees Celsius difference. And we note that information down in this table. So we say at the 0.98, its range is -3 to -2. So the temperature range where it would occur is -3 to -2. Similarly, for 0.75, you can look up the table and do this example yourself. The range is -2 to -1. 0.49, the range is again -2 to -1. So on, once we get to bottom up cracking, you have to do the same thing. So I'll just show you one example for bottom up cracking. Here we had 1.32 megapascals. Now if I go back to table 1 and now in table A, I have to look up the bottom up cracking side. So I had 1.32. 1.32 is clearly going to be between 3 degrees Celsius and 4 degrees Celsius. So that's the number I put over here, 3,4. So I've given you the range of the equivalent assumed linear temperature distribution where the same stress would occur as the actual nonlinear temperature distribution. The last step which we do is that so at the end of this we get the step C. We get a certain range of temperature distribution for each hour. So for example, in this hour we have -3, -2. In this hour we have -2, -1 and so on. So we just get a list. What are these bins? What are these ranges of the linear temperature difference? And what is its frequency? Step 4 is for each month. Again, all of this is done for each month. For each month of the analysis, a frequency distribution of linear temperature difference is thus compiled. That's basically what I showed over here. How many times do you have this -2 to -1? How many times do you have -3, -2? How many times do you have 2, 3? How many times do you have 3, 4, etc.? You can construct a frequency distribution accordingly. So for each month, a frequency distribution of linear temperature difference can be compiled. Again, done separately for bottom-up cracking, separately for top-down cracking. And in this way, the stress distribution in table C, as I've been saying, is equivalent. The amount of stress we're getting in table C is equivalent whether we use the actual nonlinear temperature distribution or the assumed linear temperature distribution. So we have constructed an equivalency still for the reference load. I still haven't come to the actual traffic yet. But for the reference load, we have constructed an equivalency between the stress developed due to the actual nonlinear temperature distribution and the stress developed for an assumed linear temperature distribution. So we might get something like this. what we have is here, we have this delta T. Again, this delta T is the assumed value. So it's at every 1 degree Celsius. For bottom up separately, for top down separately. So bottom is going to be positive, top down is going to be negative, and we get the frequency of each of those bins. So for example, this bin might be 2,3, this bin might be 3,4. For each of those values which we got in table C, so these values which we got in table C, we just calculate the frequency and we plot it into this histogram. So we get this sort of a histogram. And then from the histogram, suppose then we have a histogram as follows. Suppose based on the histogram, we get the following temperature distribution probability for that month. That is, now what I do is, for this histogram, I convert it into a probability distribution function, and I get it, suppose, at every half degree Celsius. So example, I get delta T. What is the probability of having delta T of 0.5 degrees Celsius in that table C? Maybe 0.09, 1.5, 0.3. So basically, I'm just converting my frequency distribution at roughly every half. So basically, at the middle of each of these bars, I'm just taking what is the frequency, and that gives me the probability. And the probability, of course, has to add up to 1. So again, we do this separately for top down and bottom up cracking. So then we get this probability distribution function for bottom up and top down separately for this particular month of the analysis. The last step then is, now we actually take our actual axial load distribution into consideration. So here could be, it's just an example, it's just a notion one. This could be our actual axial load distribution. So maybe for single axles, I have 70 kilonewtons, 80, 90, 100, and these are the number of repetitions I expect in that month. Again, just notional values. Okay. What we do then is, for each of those loads of our actual temperature, of our actual traffic spectrum, so each of the loads of our actual expected traffic, and then for those delta T values which we constructed out of table C, for each of them we calculate what is the critical stress using ISLAB. So example, if we know we have a single load of 70 kilonewtons, we apply a temperature distribution of 0.5 degrees Celsius, 1.5, 2.5, 3.5, so on. We apply it, and in each case we get the critical stress out of our numerical analysis program. So the values might be notionally as I wrote over here. Finally, what we get is, so we can get for each of these temperature distributions, each of these assumed linear temperature distributions, and for each of the axial load spectrum, we can get the stress. Now, each of these temperature distributions has a probability associated with it. That's basically what we had over here. So each of them has a probability associated with it. So if now we want to calculate what is the average or expected value, so it's expected value or average. I assumed all of you have taken a probability and statistics class, so you know what expected value is. We get the expected value of the critical stress as simply the summation of the stress multiplied stress at that temperature multiplied by the probability of that temperature. This should have been a delta T over here. Okay. So for example, for 70 kilonewtons, what we can do is, we will take 0.12 multiplied by the probability of 0.15 degrees Celsius. Take 0.23, multiply by the probability, stress multiplied by the probability, sum it up, and then we might get what is the expected or average value of the stress. Do that for each axial load, and then all of a sudden what we've gotten for that month, well, not all of a sudden, after all this analysis, for that month, we get that here is this is the axial load spectrum. So this is the load, this is the number of repetitions, and here is the stress. Here is the expected stress for that month. Of course, now that we have the expected stress, we can simply divide this by, say, FCR. That's the flexural strength, and then we can get stress ratio. From stress ratio, using an SN curve, we can get NF. We can divide N, this is the actual number of repetitions, by NF, and then we have successfully calculated for the month in consideration, we have successfully calculated what is the fatigue damage, which of course, as I mentioned, that concludes our mechanistic part of our analysis. Then we can go on to the empirical part and apply a transfer function accordingly. Okay. So that's what I talked about here. So the usual ME design procedure follows beyond that point. Now, some observations. Without linearization, if we did not do this procedure, then for each month, for each load configuration, the stress would have to be evaluated at every hour. So we would, at every month, we would have roughly 720 hours of analysis. And then for each of those 720, we might have to look at maybe 10, 20 different combinations of single axle loads, similarly tandem axle, similarly tandem, maybe quad if we consider those. you can clearly see that would lead to a huge number of stress evaluations. You would get trillions of stress evaluations that would have to be performed for one pavement structure. So we are still within that design loop that we are doing iterative analysis. So for each iteration of that analysis, we would have to do trillions of these simulations. That's not reasonable. That will be a very, very slow calculation. So linearization is really a way where for each of those load levels, what you can do, and I welcome you to do this later on your own, we have successfully actually reduced through linearization, we've reduced the number of evaluations such that for each month and for each load level, we have to do maybe 4 to 5 different stress evaluations. That is much less than what we were trying to do previously. So with linearization in each month, each load level needs to be evaluated only at a small number of temperature distributions, maybe 4 on the bottom up side, 4 on the top down side. This significantly decreases the number of stress evaluations. So the number of times we have to run our finite element program or a numerical model significantly decreases. It goes from trillions to a couple of maybe a lakh or so, which is still a lot, but it's better than a trillion. So, and furthermore, linearization also reduces that original problem I talked about, which is the amount of uncertainty involved in calculating hourly load repetitions. That the need to know the hourly load repetitions combined with temperature distributions, a lot of uncertainty there. That problem is eliminated through linearization. So that was where, so what we saw in the previous two lectures, we talked about traffic and we talked about climate. And in today's lecture, I showed how traffic and climate can be combined through linearization to decrease the number of evaluations that we have to perform. So now that we've done that, we basically have completed all our preliminaries and we are set to now move in the next lecture into finally doing what we promised to do, which is seeing how MEPDG actually does design of JPCP sections. So we'll talk about that in the next lecture. Thank you.